The year was 2021, and the city had traded cigarette smoke for cloud vapor. The old filing cabinets were gone, replaced by containers, clusters, and dashboards glowing in the dark. Java ran in the walls like old wiring. Web apps, payment systems, game servers, identity portals, factory tools. Everybody had a little piece of the same library tucked in a jar file somewhere. Most never thought about it. It was only logging, they said. Then December came in wet and mean. On the ninth day, a simple string started moving through the alleys of the internet. Not a password, not a weapon you could see, just text. A few crooked characters wrapped around JNDI, and suddenly servers were reaching out into the night, fetching code from strangers. The case name was Log4Shell. The body on the floor was trust itself. The target was not one company. That made this one different. The target was any application using Apache Log4j 2, a common open-source Java logging library used to record events, errors, usernames, headers, chat lines, search terms, and whatever else an application wanted to remember. Log4j was everywhere because it was useful, mature, and free. It sat inside enterprise products, internal tools, vendor appliances, cloud services, and old applications nobody wanted to touch. Before the storm, the security posture looked normal by the standards of the trade. Firewalls at the edge, vulnerability scanners on a schedule, security teams watching alerts, software bills of materials, if they existed, were often incomplete. Many organizations did not know which applications included Log4j, which version they ran, or whether it was hidden inside a larger vendor product. The streets looked quiet. But under the pavement, the whole city shared the same cracked water main. The first public flare came when attackers were seen exploiting Minecraft servers through chat messages. The vulnerable component was Apache Log4j 2, versions 2.0, beta 9 through 2.14.1. The main flaw was CVE 2021-44228, rated CVSS 10.0. It allowed remote code execution when Log4j processed a crafted lookup string such as allo jndi aldap attacker. The key piece was jndi al. The key piece was jndi al. The Java naming and directory interface, which lets Java applications look up resources through services like LDAP, RMI, DNS, and others. In vulnerable Log4j versions, message lookup substitution. Here is how the knife went in. A web server might log a user agent header, an X-forwarded for header, a login field, a chat message, or a search query. If an attacker placed the JNDI lookup string in one of those fields, and the application logged it with vulnerable Log4j, Log4j would try to resolve the lookup. The victim server would make an outbound LDAP or RMI request to an attacker-controlled host. In many exploitation patterns, that lookup returned a reference to a remote Java class or a serialized payload. The victim JVM could then load or execute attacker-supplied code, depending on Java version, configuration, and available gadget paths. The flaw class was improper neutralization of special elements in output used by a downstream component with dangerous lookup behavior. You could tie it to CWE 917, expression language injection, and CWE 502 when unsafe deserialization paths came into play. But the plain truth was uglier. Logging untrusted text had become code execution. The original bug had company. When defenders tried to close one door, more cracks showed. CVE 2021-45046 followed, first thought to be a denial of service issue, then shown to allow remote code execution in certain non-default pattern layout configurations with context lookups. CVE 2021-45125 covered uncontrolled recursion that could cause denial of service. CVE 2021-44832 involved JDBC appender configurations where an attacker with control over the configuration could trigger remote code execution. Apache moved fast, shipping Log4j 2.5.0, then 2.5.0, then 2.5.0, and later 2.5.0, and later 2.5. The safest line became clear. Remove the dangerous lookup behavior, disable JNDI by default, and upgrade to a fixed version. But by then, the alarms were ringing from every block. The perpetrators were not one gang. That was the devil of it. Once the exploit went public, the street filled up. Crypto miners moved first, dropping XMReg and other Monero mining payloads to turn stolen CPU into dirty money. Botnet operators folded the exploit into Mirai variants and other malware, hunting Linux servers and internet-facing appliances. Ransomware affiliates tested the doors. Access brokers looked for footholds they could sell. Nation-state teams joined the crowd. Microsoft reported activity by groups linked to China, Iran, North Korea, and Turkey. The Belgian Ministry of Defense confirmed an incident. VMware Horizon servers became a favored target later, with Iranian actors and ransomware crews exploiting Log4j and internet-facing Unified Access Gateway and Horizon environments. After initial code execution, the second act depended on the victim. On Linux, attackers often used curl or wget to pull shell scripts from command and control servers. Those scripts killed competing miners, downloaded binaries, created cron jobs, added SSH keys, or planted web shells. On Windows, intruders used PowerShell, Certudal, Bitsadmin, or Rundle32 to fetch payloads. In enterprise cases, the foothold could become a beachhead. Attackers dumped credentials with Mimikatz or LSASS memory access, searched file shares, queried Active Directory, and moved with CXSec, Windows Management Instrumentation, Remote Desktop Protocol, or stolen VPN credentials. Living off the land made the footsteps lighter. A process spawned by java.exe should have been suspicious when it launched bash, she, PowerShell.exe, cm.exe, or curl. Too often, it blended into the city noise. Persistence came in many coats. Some crews planted scheduled tasks or cron entries that called back to attacker servers. Some added new users or SSH authorized keys. Web shells were dropped into writable web directories. Malware used systemed services, init scripts, registry, run keys, or startup folder tricks. In cloud environments, attackers looked for instance metadata services and environment variables, hoping to steal access keys, tokens, and secrets from the host. If the compromised application had generous permissions, the blast radius grew fast. A single vulnerable Java process could become a doorway into object storage, databases, message queues, or deployment pipelines. Exfiltration and command control were just as varied. The simplest scans used DNS callbacks to prove a target was vulnerable. Services like Interax, Ekechi, Burp Collaborator, and Attacker controlled DNS domains helped operators see which servers reached out. More serious crews used LDAP and HTTP servers for payload delivery, then shifted to encrypted C2 channels over HTTPS, Telegram bots, Tor hidden services, or commodity malware panels. Some intrusions ended with mining, others ended with data theft. The initial string was tiny, but the haul could include credentials, source code, customer data, cloud keys, and internal documents, depending on where the door opened. The detection failures were the kind that make a detective stare into his coffee. Many firms did not log outbound LDAP, RMI, or strange DNS calls from servers that had no business making them. Endpoint tools sometimes missed child processes from Java runtimes. Vulnerability scanners failed when Log4j was shaded, repackaged, or buried inside fat jar files. Asset inventory was the first casualty. If you could not name every application and dependency, you could not know where the fire was burning. The damage was measured in long nights and hard numbers. The vulnerable library affected millions of applications and services across the world. The Cybersecurity and Infrastructure Security Agency called it one of the most serious vulnerabilities it had seen. Tenable estimated that a large share of organizations had exposed Log4j-related risk in the months after disclosure. Cloudflare, Akamai, Microsoft, Google, Cisco, Amazon, Apple, IBM, VMware, and countless others hunted through their stacks. The direct global cost is hard to pin down, but remediation ran into billions when you count emergency patching, vendor response, incident response, retainers, downtime, overtime, and delayed projects. The human impact was not always a headline breach with names in a database. Sometimes it was smaller and meaner. Hospital IT teams had to scan systems while care went on. School districts hunted vulnerable services with thin staff. Small businesses waited for vendors to tell them if the cash register, router, or customer portal was at risk. Executives learned that an open source component maintained by volunteers could become a board-level crisis overnight. Governments issued emergency directives. CISA created a public Log4j scanner and a community guidance page. The Federal Trade Commission warned companies that failure to patch could lead to legal action. The rain hit everybody, rich and poor alike. The case changed the way defenders talked about software supply chain risk. Log4Shell proved that dependency risk is not academic. It lives inside builds, containers, appliances, and managed services. The controls that mattered were plain. Maintain a real asset inventory. Keep a software bill of materials using formats like SPDX or CycloneDX. Track dependencies with software composition analysis tools such as Snike, Mend, Black Duck, GitHub Dependabot, OWASP Dependency, Check, or similar systems. Use CI and CD gates to block known critical flaws. Sign and verify artifacts with SigStore, SLSA practices, and trusted build pipelines. Know what you run before the city catches fire. For prevention and detection, the answer is layered defense. Upgrade vulnerable Log4j versions and do not rely on string filters alone. Remove dangerous components such as J&I lookup, only as a temporary measure when patching cannot happen fast. Apply egress filtering so servers cannot call arbitrary LDAP, RMI, DNS, or HTTP destinations. Segment networks so a web tier cannot wander into domain controllers and databases. Use MFA for administrative access. Deploy EDR that flags java.exe spawning shells, PowerShell, curl WG, WWS for strange callback patterns. Centralize logs in the CMWDNS for strange callback patterns. Map detections to MITRE-AT and CK techniques such as command and scripting interpreter, ingress tool transfer, credential dumping, and remote services. Practice zero trust, not as a slogan but as a habit. Least privilege, strong identity, continuous verification, no soft doors left open because the lobby looks clean. That is the file on Log4Shell. A single string walked into a logging library and came out holding keys to the city. The old lesson still stands under the street lamp. In this business, the quietest dependency can cast the longest shadow.